Hi, welcome to another of our LTS webinars. We're very happy to have you here. Just before we begin, I would like to explain real quick the Q&A modus. And so at the bottom of your screen, you will see a Q&A icon. If you click on it, you can enter the question at any given time. However, due to time constraints, we'll allow questions to be answered only during the last 10 minutes. Questions that go unanswered will be answered later by email. And without further ado, it is my pleasure to introduce Wolfgang Strasser, our diagnostics expert.
My name is Wolfgang Strasser, and I'm leading the diagnostics area within the connected mobility practice here at Luxoft Automotive. We are very excited having the chance today presenting to all of you the diagnostics topic, where we are now and where diagnostics is going to. So this is what we are going to present today. Do we have the slides already? Okay, hopefully. So first of all, I would like to tell you some more details on our connected mobility practice. After that, I would like to hand over to my colleagues Markus and Tarkan, which will guide you through the topic of diagnostics itself. As we have here a very wide audience with different levels of knowledge, we would like to give you a short introduction into vehicle diagnostics first. If you are already into this topic, please be patient. The more interesting parts for you will follow in a couple of minutes. We have split up the topic of diagnostics in different chapters, talking about onboard and offboard diagnostics, different technical approaches, and finally also on topics where we see the future of vehicle diagnostics. So let's start with just a few words on our connected mobility practice. Luxoft Automotive is in general divided into different departments, which are called practices here. The connected mobility practice of Luxoft Automotive is covering all the topics where the vehicle is communicating, let's say, with the outside world. Our practice is separated into different technology areas, which are cybersecurity, telematics, connected solutions, and also diagnostics, of course. In each technology area, we are building a strong expertise on the corresponding knowledge domain. This enables us to execute customer projects in this connected domain as per demand of the project. This way, we are able to pick out required knowledge out of the different technology areas and build a strong project team. And of course, we are also working together with our other practices, which are digital cockpit and autonomous driving. So that's it already for the connected mobility practice. So Markus, please go ahead.
All right, thank you, Wolfgang. Hello to all and welcome to the webinar Diagnosis. What is today and what will come tomorrow? First, I want to introduce myself. My name is Markus Schnurrbusch and I'm working in the diagnostic area for 16 years now. The first 6 years of my career, I was working in aviation diagnostics, diagnosing and repairing aircrafts. And since then, I'm working in the automotive diagnostics area. All right, so let's start. First, I want to go over the definition of diagnostics. As a first step, let's see what the definition of medical diagnostics is. Medical diagnosis is what a doctor does when you're sick. Through examination of your symptoms, pains, and overall condition, he gathers information about your health status and which hopefully leads to a proper treatment. So now, vehicle diagnostics is pretty much the same. The goal is to determine a faulty mechanical or electrical component inside the vehicle by collecting information about the vehicle's health status through error codes, in short DTCs, through visible symptoms, or even by the experience of a workshop technician. And if your vehicle is in a workshop, this should be done as fast as possible. Well, to do this, we need to be able to connect to and read all necessary data from within the vehicle. All right, Tarkan, can you tell us a little bit about the automotive history?
Yes, sure, Markus. But firstly, I want to introduce myself. Hi, everyone. I'm Tarkan Uener, and I'm working for Luxoft as a requirements engineer and diagnostics area too. So let's have a look into history going forward until today, and let us speak into the future. Carl Benz invented his Motorwagen Nummer 1 in 1866, and shortly after that, the first automotive vehicles were on the road. There were only a few of it, and in terms of complexity, well, I think it was manageable. If we are talking about diagnostics, now, well, back then, a wrench and a screwdriver should have solved most of the occurring problems. A few years later, in 1913, Henry Ford invented the first assembly line. This was the start for vehicle mass production. While the number of vehicles on the road increases, the technical complexity does as well. More cars, more complexity. Yeah, the workshops were born there. So the vehicle owner had a place where they could bring their cars in case something got broken. Of course, the workshop technicians still used a wrench and a screwdriver back then.
All right, so let's make a jump to the middle of the 90s. Somewhere at this time, well, plus minus a couple of years, the first electronic components have arrived inside the vehicles. The electronic control units, or in short, ECUs. At this time, a workshop technician was now dependent on additional tools, besides a wrench and a screwdriver, to diagnose his vehicle. The first computer terminals were seen in the workshops. They were huge, big, and inflexible. And the vehicle needed to be connected to such a diagnostic tester via an electrical cable. In the next 20 to 25 years, the automotive industry made some huge technological leaps. Diagnostic tester got smaller, fitting now on a laptop or even on a tablet. Cable connections are mostly replaced by wireless LAN. With the technological progress, with the technological progress, new functionalities are brought into our vehicles. Assistance systems like collision warning, cruise control, rear view camera, lane departure, and so on. They are not only nice for the user, but also increasing the complexity of a vehicle. Autonomous driving is probably the best known vision at the moment. I'm pretty sure everyone in the audience has an idea of what that means in terms of computing power inside a vehicle. So I would like to show on a simple example how complexity is increasing inside a vehicle. The VW Golf number 1 had 191 wires included with an overall length of 214 meters. The VW Golf number 7 has nearly 1,000 wires with an overall length of 1.6 kilometers. In general, a modern vehicle includes around about 100 ECUs. Of course, an upper class vehicle has a little bit more. So coming back to computing power. For a very long time, we had, and we still have, those ECUs. Electronic units running a piece of code, simplified, able to control input and output pins. Each ECU responsible for one function in the vehicle, like transmission control or engine control. With functions increasing exponentially inside a car, we have now two choices. Either we stick with technology older than 25 years, where we would need much more than hundreds of ECUs, not mentioning the weight of those, or shifting the functions into a much more contemporary technology. And that's what automotive industry is starting to do. Now, talking about diagnostics again, what impact does this have for us? Well, firstly, much more stuff can break. And second, much more data out of the vehicle is available. And third, we need to handle all those data to do a proper examination on the health condition of our patient. But with all these great new possibilities, we should not forget to be able to diagnose, well, a senior vehicle as well. And how we bring all these together, that's something we will explain a little bit later. All right, Tarkan.
So, for now, let's have a look into the far future. Autonomous driving will be water under the bridge very shortly. Well, maybe sometime in the future, we will have flying cars, UFOs, who knows? And how to diagnose them, we will see. But we are laying the foundations for it now. So let's move on to offboard and onboard diagnostics. How to define offboard diagnostics? Well, you can say offboard diagnostics is everything related to diagnostic outside the vehicle. Well, you can say offboard diagnostics is everything not in the car. This everything, of course, includes data out of the vehicle, but also the vehicle's history, accumulations of problems within the vehicle fleet, and last but not least, the experience of a workshop technician. A diagnostic tester, for example, has predefined test sequences to guide a workshop technician through a couple of test steps to determine a faulty piece of hardware based on error codes or symptoms, which are either read out of the vehicle or manually entered by the technician into the test software. But how will those predefined test sequences land up in a diagnostic tester? There are a couple of areas which have to be considered. Definitely, you will need a diagnostic tester for your workshops, but also will need a tool to generate those test sequences running on your diagnostic tester. So the so-called diagnostic authoring tool. You will need guidelines on how to create these test sequences. You need trained and skilled people to create the test sequences. Before forwarding your diagnostic content to the workshops, you have to test it. I think it's clear that a huge amount of data will be created in this context. So therefore, a data management system has to be in place so that everyone can work on it. And of course, all of the mentioned points need to follow a process. Within the diagnostic team of Luxoft, we have experience and the knowledge to provide exactly that to our customers.
All right, let's go to the next topic, onboard diagnostics. So previously, Tarkan said offboard diagnostics is everything related to diagnostics outside the vehicle. Well, onboard diagnostics is everything related to diagnostics within the vehicle. So on a high level, all ECUs that a diagnostic tester can talk to and which provide a diagnostic interface for, reading diagnostic relevant information, controlling actuators from within a diagnostic tester, writing values into an ECU, and so on. Furthermore, all logic inside an ECU, monitoring the input and output pins, controlling them, evaluate and store a DTC within the fault memory, providing functionalities to update the ECU software. Well, I think you get the picture. So the onboard diagnostics, part of an ECU software, as well as the ECU software itself, is nowadays mostly implemented within AUTOSAR, an OEM-wide standardized development platform. To get everything working for a productive environment, of course, you need to test all those parts as well. And we at Luxoft are providing this as well to our customers.
So let's now move on to technical approaches. Let's have a look into the old-fashioned classical diagnostics. Gladly, nowadays, we have a laptop or a notebook where a diagnostic tester is running on. The diagnostic application has all the diagnostic knowledge. As an example, all test sequences, all information on how to read data out of an ECU, or on how to control actuators within an ECU. But that's not enough. All those information needs to be interpreted. A diagnostic application needs to know how to communicate with an ECU. The automotive industry faced this problem quite some time ago, and standards were defined, a couple of them, meanwhile, as an ISO standard. Test sequences, test logic can use ISO 13209, also called OTX. OTX means Open Test Sequence Exchange, a standard to create test sequences in an exchange way. Communication, bits and bytes versus human readable form are defined in ISO 22900-3, also known as ODX, Open Data Exchange. Putting bits and bytes together, adding all necessary additional information to it so that the message can be sent over a bus system is defined in ISO 22900-2. All these pieces in combination represents a diagnostic tester. On the other hand, we have our patient, so in that case our vehicle. In classical diagnostics, a vehicle consists of engines, mechanical components, electronic control units, wires for tires, and wheels. The ECUs are connected through several bus systems, all connected with a gateway. The diagnostic tester can be linked to the gateway either via CAN bus or via Ethernet. So if the linking is completed, a diagnostic tester can request a specific piece of information from an ECU. The gateway will route the request to the addressed ECU. The ECU will answer accordingly back to the gateway, which will forward the response to the diagnostic tester, where the data will be evaluated. Markus.
Well, right. Thanks, Tarkan. So now let's see. Right. So what are the short-term upcoming challenges an OEM will, or is already facing? Let's have a look in remote repair. The use case behind remote repair is mainly customer satisfaction. Nothing is more annoying than having your car in a workshop and you sitting around for hours waiting till the repair has been completed. With remote repair, OEMs want to support their clients on the road remotely by analyzing the vehicle's condition, running test sequences, and so on. So with the goal either to fix a problem directly or at least to give the information on how serious the problem is, meaning if the customer can continue his drive or has to go to a workshop immediately, whereby spare parts, for example, have already been ordered from the help desk. Next point would be remote production. So this is actually relevant for the car manufacturers. With this function, an OEM wants to have access to the vehicle when it is already off the production line. So for example, because a wrong ECU software or a wrong coding string was detected, but it cannot be fixed during production without any further impact to the rest of the production line. So in this special case, the OEM can then easily, remotely from anywhere, update or write new coding values into the car, even if the car is somewhere on the parking lot. Remote update. Well, I think we all know this scenario, being somewhere and suddenly your mobile phone or tablet wants a software update. So meanwhile, all devices that are wireless connected to the internet can do this. But why not vehicles? With remote update, you can perform software updates on your car without the need to go to a workshop. For example, during the night when your car is in the garage. And this saves you time. And of course, it saves you money. So next point would be function on demand. Well, that may not fit in this area firstly, but you will see it does. So let me explain to you why. In vehicles, there are different functions, which can also be changed by the workshops, of course. However, this is time consuming. And what if the customer is currently abroad or has no workshop available? So let's take a look at a vehicle, for example, with an automatic tailgate and a luggage box on the roof. Well, normally the tailgate would open to 100%, yeah. But in this case, with the luggage box on top, the box would get damaged. So in this case, you might contact the help desk and they can easily change the opening engine remotely so that you don't harm your car, of course. The next point, what we see here are, well, apps. Yeah. Well, I don't have to say much about apps. Everyone knows and uses them. This function should give the customer the possibility to load apps into the vehicle, well, or update them, yeah? Only by confirming the relevant update or the relevant download. So let's move to a really exciting part of future diagnostics. Tarkan.
So in my opinion, that's one of the most exciting ones, the predictive diagnostics. First, failure avoidance. At the moment, our vehicles can detect that there is a problem and show us through, depending on warning message on the display or a light, that the car has to be checked out. But what if we can detect early on before an error occurs and so avoid major damage, for example, in the engine? Predictive diagnostics simply aims to achieve this failure avoidance. Therefore, remote support and updates should be realized. Now the car has recognized that there may be a problem in the near future, whether this is now in the engine or on wearing parts of any kind. The idea is that after this detection, the help desk will proactively contact the customer and tell him or her, step by step, how to proceed. To simply avoid major damage before it even arrives, or to save the customer the trouble of stopping on the highway, in my opinion, that's really beneficial. So let's move on to customer understanding and sensitivity. We all know Siri or Alexa, artificial intelligence is all around us. To keep with the fast-moving time and make the car more interesting, customers should realize that we pay attention to their needs. I would like to explain this, well, let's say in an example. Imagine that you are driving your car and suddenly you hear a voice talking to you. Yes, it is your car. It detected an issue regarding the engine functions. But since this is predictive, you don't have to go to the next workshop as soon as possible. It is giving you time to schedule a meeting. So I think now we are approaching smart cars that adapt to the driver. Isn't it like future music? Okay, last but not least, let me say some words about development for manufacturers. Predictive diagnosis would also lead to a productive increase in development for OEMs in order to avoid large product recalls, to increase customer satisfaction, and also to reduce costs. This enables a manufacturer to recognize early, for example, that a cable harness is too close to the motor, which, as we all know, can become very hot. This cable would be damaged sooner or later. But recognizing that early, the OEM can automatically stop further models in production to eliminate these issues. Well, that was remote and predictive diagnosis. Let's move on to the technical approach in vehicles. Technical progress in cars already started and is always going on. The smart devices will soon replace the diagnostic testers or off-board testers. This means that the diagnosis of vehicles will be able to display on different devices, such as smartphones, tablets, or even normal notebooks. The currently known diagnostic logic, which runs on the tester, will also be located in the vehicle now or then. This conversion from an off-board tester to a full functional onboard tester leads to vehicles diagnosing themselves. However, some new hardware systems will ensure that the self-diagnosis also works. Here, for example, high-performance computing platforms could get into the car, and it will take control. Means that all runtime functions like OTX, ODX, etc. are now running in the vehicle. ECUs will, of course, not completely disappear from the car. The information generated by the vehicle will be sent then to the cloud in the backend. For that, you need a cloud, of course. And this can be done from anywhere over the air. To send the data to the backend, a connected gateway is required, which is also placed in the car. No matter where the vehicle is, it can send diagnostic data. This data can be read out and processed by the various end devices at workshops or at the help desk. So this leads to exciting challenges because the architecture for this should be created. As we can see, more and more technologies are being introduced into the vehicle in order to better control the diagnosis. But more functions also means that we need new, better diagnostic approaches. Let us take a closer look at the diagnosis of the future and the challenges to which we are creating solutions. Markus, would you please go on?
Well, all right. So let us talk about a new diagnostic approach, which fits into the latest and future vehicle architecture and is able to handle the complexity and the huge amount of data from within the car. Well, the keyword here is service-oriented diagnostics. But firstly, we will have a view on the vehicle's architecture and the changes in there. So for certain, most of you already know that there is a fundamental change ongoing within the automotive industry. The target is to reduce the huge amount of ECUs inside a vehicle. Well, ECUs still have their place and their authorization within a vehicle architecture. But they might get simpler, being reduced to the minimum of needed electronics so that they can control input and output pins only. So let's focus on the middle part of this slide, HPCs, high performance computers. I think this is one of the most significant change inside the new vehicle architecture, and the change has already been started. So these high performance computers are creating the possibility to shift functionality away from the ECUs into themselves. They have much more memory than a simple ECU, and the computing power is, let me phrase this in terms of a comparison, an ECU is an old donkey, as well a HCP is a racehorse. So with this technological change, OEMs are now in the position to add even more functionality into the car. Highly complex functions like advanced driver assistance systems, here we go, which are communicating to each other, which are depending on each other, well, they're bringing us one step closer to autonomous driving, or in the future to flying cars, who knows? Okay, so of course, one high-performance computer will not be enough inside a vehicle. We need several of them inside the vehicle. Well, not 100, like we have ECUs now, but 4 or 5 or 6, yeah, I think that could be enough for the moment. So definitely, the high-performance computer needs to talk to each other. And for our new diagnostic approach, covering all functions and use cases mentioned before, they need also talk to the cloud. So how they are communicating to each other, what they need to provide, and or what they can expect from other HCPs is part of the middleware, which we as Luxoft also take part in to design. By changing the vehicle's architecture, or the vehicle's hardware architecture, to be correct, OEMs are also enabled to change the vehicle's software architecture. And one approach here is to change the system to a service-oriented architecture. A concept here, which is already well established in the IT domain. One benefit of using the service-oriented approach in automotive is that the same technology which is used within the vehicle can also be used to communicate to the outside world. And through this, it is very easy to exchange data between the components of the vehicle and the backend, or other external devices like smart devices or even a charging station. So for diagnostics, what does that mean? Well, we want to do also service-oriented diagnostics here. Okay, so now we had a deeper look into the changing vehicle architecture. So let's focus now on service-oriented diagnostics and how it could look like. So as for now, service-oriented diagnostics is a white paper with some brush strokes on it. The good news here is we have the brush in our hands and we can design and change it as we need. So, well, let's see. The vehicle could provide an entry point, for example, a diagnostic service, which allows the access to all diagnostic relevant information and functions. The diagnostic service itself could be a composition of other useful services like error logging or data collector, diagnostic job service or an update service, and many, many more. As the classical UDS ECUs will not disappear immediately within the vehicle, the in-vehicle tester approach, which we saw before, can still be used to access the old-fashioned diagnostic world. A backend system or other components like smart devices could easily communicate with the vehicle using established protocols like MQTT or RESTful protocols. So let's point out some benefits of a service-oriented diagnostic approach. Well, the cloud access could be done via one central onboard diagnostic service. So there will be only one entry point to the vehicle, and only one entry point needs to be secured. And it allows the usage of scalable state-of-the-art technologies for communication like HTTP and so on. Another benefit would be that a service facade could encapsulate the classical diagnostic, meaning old tools can still be used for engineering and for testing and production of microcontroller platforms, whereby new tools can start using the service approach. So this service approach would make it pretty easy to change diagnostics features just by adding or deleting services out of the feature itself, like changing the update behavior or how configuration is done inside a vehicle. And this can be done on business demand. So automotive industry is changing quickly. Nevertheless, we cannot make a hard cut in diagnostics as the changes are done very softly. But with the service-oriented approach, we still can use the classical technologies and processes, and this as long as necessary. All right. Okay. So we have one topic left. That's AUTOSAR. And therefore, I'm going to hand back to Wolfgang.
Yes. Thank you, Markus and Tarkan. Okay. So one other exciting topic in this context is also adaptive AUTOSAR. So first of all, let's have a short overview here as well. So for those who don't know, what is actually AUTOSAR? Basically, AUTOSAR is a worldwide development partnership of automotive interested parties founded in 2003. So please go ahead with one more slide, please. You can see here the core partners are mostly OEMs like BMW, Ford, Volkswagen, and others, as well as the tier ones, Conti and Bosch. Beyond the core members, there are the premium and development partners, consisting out of some OEMs, tier ones, and also suppliers like Honda, Renault, Denso, Vector, and others. And also we as Luxoft are contributing here as a premium partner. So now, what actually does the AUTOSAR group? The AUTOSAR group has a target to define standards for the automotive world. So the main contribution of the AUTOSAR group so far was the AUTOSAR stack, or how it is called now, the AUTOSAR Classic platform. The AUTOSAR Classic platform is a software framework that is used within vehicle ECUs. Basically, it provides some software modules for common core functionalities of an ECU, like communication, memory access, cryptographics, or also diagnostics, and as well others. AUTOSAR Classic is built for microcontroller-based ECUs. The scope here is dealing with limited resources and real-time execution. If you are now implementing a certain vehicle function, you can easily use all of these software modules and, of course, focus on the actual functionality of the vehicle function you want to implement. The next and currently still ongoing step of AUTOSAR is the AUTOSAR Adaptive Platform. There are certain upcoming demands from the automotive industry that cannot, or at least not very well, be covered by the AUTOSAR Classic platform. For example, efficiently using the resources of high-performance computers, as described before. Integrating third-party software to the system, like Google Car, for example. Flexible software configurations or dynamic functions. So, for example, shifting a vehicle function during runtime from one ECU to another. That's why in certain areas, microprocessor-based systems with some Linux operating system are already used. For example, usually in infotainment ECUs. I don't want to address all points of the slide here in detail, but the most important point is AUTOSAR Adaptive now brings the classic AUTOSAR stack into the POSIX, or actually, let's say, the Linux world. So that means you're able to write applications for Linux and use the provided functionalities out of the adaptive framework, which is quite similar to the classic one. So the first rollout of AUTOSAR Adaptive was in March 2017, so last year. And currently the AUTOSAR group works on two things. On the one side, improving and finalizing the specifications, and on the other side, also doing a reference implementation. So in difference to classic AUTOSAR, there were only specifications provided. The actual implementation was done by tool suppliers like Vector or Electrobit. For AUTOSAR Adaptive, it is now different. The AUTOSAR group works also on this reference implementation. And we, as Luxoft, are contributing here as well in terms of specification as well as implementation, including the diagnostics area within adaptive. The challenge here is now to bring these things together with the service-oriented diagnostics as described before. For the moment, this means creating service-oriented adapters for accessing the diagnostic modules of AutoSAR Adaptive. In the long run, it should be the target to bring this service-oriented approach also into the adaptive standard itself. So now we are actually coming to the end of our presentation, but maybe just a short summary. So this is where we think that the future of vehicle diagnostics is going to. Using new software frameworks for automotive, like the AutoSAR Adaptive platform, and having service-oriented communication and also service-oriented diagnostics within the vehicle and to the outside world. This is what vehicle diagnostics will look like in future, and we are working on it. This way, we are able to fulfill the requirements for use cases like remote repair, remote production, software update over the air, and also provides a basis for future topics like predictive maintenance. So, yes, thank you. That's it actually so far from our side. We hope you enjoyed our webinar, and yeah, if you have any further questions, please feel free to raise them now. So, thank you. Yeah, at least we have got one question, which is whether the webinar will be available as video afterwards. So this is usually the case. Yeah, you can find it, I think, on our webpage. Yes. Are there any further questions? So I don't think so, at least for the moment. Then thanks to all of you, and yeah, bye-bye.